Let us continue with the second talk of this afternoon. It's a pleasure to present Jessie Pontigo from here, a local speaker, who will speak about an overview for the infinitesimal versions of Hilbert's 16th problem and the Poincaré center focus problem.
Hi. Thank you very much for the invitation and for giving me this opportunity to share with you the research we are working on. So, let's start. And this is the plan. So I will introduce the classical problems, and then I will go to the infinitesimal versions, and then I will explain some techniques we use in this to study this kind of problem. And then I will focus on some research we're working, which is still in progress. And that's it. So let's start with the original classical problems. So there are two problems which are very similar. They go parallel. And the first one is the Hilbert 16th problem, which is the problem about limit cycles. So you have a planar differential equation, polynomial, and you ask about how many, an upper bound for the number of limit cycles this equation can have, but in terms of the degree of P and Q. Yeah, this was a problem proposed by Hilbert. This is one of the problems in the Hilbert list. And also, almost at the same time, Poincaré proposed this problem, which is also we have a polynomial planar differential equation. Now it's the problem to give conditions in order to have a center singularity. Yeah, just to remember, limit cycles are isolated periodic orbits, and center singularity is a singularity which is foliated by continuous family of periodic orbits. And these two problems were proposed almost at the beginning of the 20th century, and they still remains open. The first one is completely open. We still don't know if this bound exists. And the second one, we know the solution for the case of degree 2. It was given by Dulac, but for degree bigger or equal to 3, we don't know the conditions. So in order to understand a little bit these problems, then the infinitesimal version arises. And the infinitesimal version is not to deal with the whole world of polynomial differential equation, but only with those who are given by this perturbation. So we start with a Hamiltonian one, like this, and those are the simplest but not trivial planar polynomial equations in terms of the behavior with respect to limit cycles. They don't have limit cycles at all, but once you get this perturbation, here epsilon is just a small parameter. P and Q are polynomial, and then you ask for an upper bound for the limit cycles that can arise after the perturbation. So we start with this situation. Imagine you have an annulus neighborhood foliated with periodic orbit, continuous family, and after the perturbation, you can end up with something like this. Some of the periodic orbits can remain as periodic orbits, but most of them will break. And so you will get some isolated periodic orbits. That is, you will get some limit cycles, and so you count how many of them you get, and then you have you want to have this upper bound. Okay, but in terms of the degree, this is the difficult part. Okay, if you have any questions, you can stop me at any moment. Well, this is the infinitesimal version for Hilbert's 16th problem, and for the infinitesimal Poincaré center focus, it's very similar. Also, you start with the Hamiltonian equation, and you perturb the equation. And now, instead of having this situation, you will like to have only periodic orbit here, not limit cycles at all. Okay? Here, both problems, they are actually topological questions. No? You are dealing with either you will break these periodic orbits, or you will, they will remain as periodic orbits. So we can just work with the defoliation, which means we don't care about the parametrization of the solution, just the solution as sets on the plane. Okay, so I will use this notation. This is the equivalent notation for the vector fields. And now with this notation, this will be useful later for computation. So that's why I'm introducing it. And now the problem reads like this. We have this perturbation of a Hamiltonian differential equation or a Hamiltonian foliation, and we want either the upper bound for limit cycles or the condition to preserve the periodic orbit, the whole family of periodic orbits. Okay? So those are the main problems. And let's see some tools that we used to use to study these situations. So the first one is what is called the Poincaré first return map. Maybe I will draw a little bit because I will use it later. And so first we have this annulus foliated with periodic orbit. This is the Hamiltonian foliation. And then we make the perturbation. So some of these periodic orbits remain, but some of them will be broken. And we consider here a transversal, we'll call it tau, transversal to this family. And after a small perturbation, transversality is very stable. So this is again a transversal for small perturbation. Here we are on the perturbation. Okay, and some important point here is in this annulus, I don't have any critical point. Everything is regular. So we can parameterize this transversal with the values of the Hamiltonian in such a way that I will introduce this notation. Let's say that this point corresponds to the level T0, and then the periodic orbit passing through this point, I will call it gamma of T0, and it means that it is contained on the T0 level of the Hamiltonian. I will use this notation. Also, it means that the Hamiltonian restricted to this transversal is identity. No, it's parameterized with the values of the Hamiltonian. And here I will write exactly the same I have in the slide. So I have this point T. The first return map is just you go around a solution of this foliation, and you associate the first point at which you arrive for the first time again to this transversal. So this is what we are calling a P gamma epsilon of T. Okay? And this is a analytic function, so we can write it with a power series. With respect to powers of epsilon. Okay, and so the fixed point of this transformation, they will correspond to the periodic orbit you get after the perturbation. But if some of these functions does not vanish, then you will get something that is not periodic. Okay, so we can codify the whole problem with this Poincare first return map. But sometimes it is useful also not to work with the first return map, but with this displacement map. And I will write it here also. This is the displacement map with respect to this continuous family of periodic orbits. And okay, here I'm assuming that maybe it does not start with M1. If it is not identically 0, at least you know one of these functions that I forgot to say. They are called Melnikov functions. Also in the literature, they call them sometimes Poincare-Pontryagin functions. Okay, so here I will call them Melnikov functions. If it is not identically 0, it means that at least there is one first non-zero Melnikov function, and it will be very important. And on the other situation is this situation corresponds to having limit cycles, and this situation corresponds to preserving the center. Yes, to preserve the center, you need that all the Melnikov functions are identically 0. Yeah, identically 0. But in this situation, upstairs, we have this theorem given by Pontryagin that tells us that if you want to find an upper bound for the number of limit cycles, it is enough to find an upper bound for the number of zeros of this function. Then you can just start studying the number of zeros of this function. And also here is with multiplicity. Okay, so we can restrict now. Our problem before was a limit cycles, then it was studying the zeros of this function, and now it is just studying the zeros of this function here. Okay, but in order to study the zeros of this function, we need to know how this function is, and also for this situation, we need to characterize these functions. This is the next step. Also, Poincare and Pontryagin gives the solution for the first order, and it turns out that it's always given by this expression, where eta, remember, was the perturbation. Okay. And since we have already the first order Melnikov function, then we have some other versions of the problems, which are called the tangential versions. It is either to find an upper bound for, this is called an abelian integral. To have an upper bound for abelian integrals in terms of the degree of the Hamiltonian and in terms of the degree of eta. Or to give conditions in order to have this function identically 0. Okay? Maybe I can give an idea of the proof. Let me write this here. Let's integrate along this cycle. Let's call it gamma epsilon. When epsilon goes to 0, this cycle goes to gamma here. Okay? I will integrate along this cycle, but since this is tangent to this differential form, this integral is equal to 0. Yeah, this is part of the foliation, so we have here the 0, but also we can write it, we can separate the integrals. So we have this situation, and I will put this here. This is minus epsilon times the integral of eta along this cycle. But this part, this is just f on the at the beginning and at the end of this cycle. So it is f of the Poincaré first return map minus f of t. It's equal to minus epsilon eta along this cycle. But we said that we are using this parametrization, so this is just, I can erase f. We have this equality, but this is just the displacement map. Yes, and the displacement map was given by the Melnikov functions. So we have the correspondence between the coefficients of epsilon, and so we get this, it's equal to, well, after going epsilon to 0. Okay, so we have this equality. Okay, so let's continue. I don't know if there is any questions now. No? Okay. Okay, so we had some simplified versions, no? which are the tangential versions. And for the tangential version, there are some upper bounds already. One was given by Benjamini, Novikov, and Jakobenko in 2010. And they provide an explicit upper bound for the number of limit cycles. And it is given by a double exponential, which is here, of a polynomial term depending on the degree. Here it's eta, it's the same, well, omega or eta. It's the perturbation. And it is the first explicit Hilbert bound, let's say. But it is not an optimal bound, but still, it's the first approximation to Hilbert problem, I guess. And 1 year later, Benditkis and Novikov also gave an explicit upper bound, not for M1, but for the higher order Melnikov functions. And in that case, you get also an explicit bound, which is also given by a doubled exponential. I didn't write it here. But the new thing here is that here the explicit bound depends on the order. I will explain later why it depends on the order. It is given by the expression of this function. But well, here we can see there are some solutions already. So let's continue. Now I want to introduce some of the techniques. We need to also to use the complexification of the problem, because for the well, we will need this complex analysis and some geometric aspect of the foliations. So it is, in order to arrive to this kind of a theorem, we need to use the complex tool. So it means that the polynomial now, it is we can see it as a function from C2 to C. It is given by the same expression, but now we just get a bigger space. And now these level curves, they are not real anymore. They are complex lines. That means they are Riemann surfaces. Okay, this is just the real part of the Riemann surfaces on C2. And this is very useful also because we have this theorem, this is the Milnor fibration, which tells us that if we take out all the set of critical points, we end up with this locally trivial topological fibration, which allows the following thing, which is crucial here. It is called the monodromy. So as I told you, now the level curve is given by a Riemann surface. It could be a torus, like here. And since it is a topological fibration, for any regular value, you have the same topology. You only have torus, but over the critical points, you have some deformation of the topology. Here, these cycles, the green ones, they collapse into a point. And they are called vanishing cycles because they vanish when you approach to some critical point. And here, the important thing is what is happening with these cycles inside these Riemann surfaces. They will tell us some information about the Melnikov functions. What is happening here is, although, well, the topology is not changing, but these cycles, they will change when you go around a critical point. And for example, here, this yellow cycle, if you go around this critical point, this start making a deformation, and when you return to the initial point, you will get that this yellow cycle goes also around it has trapped the green ones, because it's happening locally. It's happening something like this. So you start with this cycle, but at the end you also go around the green cycle. So it gives us something that is called the monodromy action. So if you go around some critical point, you will get something not trivial on the first homotopy group. So you start with a cycle, and you go around all the critical points, and you will end up with a new subgroup of the first homotopy group. In this subgroup, we will call it the orbit under monodromy. And also, this will allow us to make analytic continuation of the Melnikov function. It would make the analytic continuation easy. If you go around a critical point, this is just changing the cycle to the new one that you get after the monodromy. Okay, so you can like codify this analytic information into a geometric information. Okay. I don't know if there is any questions. No, no. Well, and what can we do with this monodromy thing? It turns out that under some generic conditions, this orbit under monodromy, with this orbit under monodromy, you can actually get the whole first homotopy group. You get everything. It means, in terms of the analytic continuation, that, for example, if you start with this abelian integral, which corresponds to M1, then you get that this abelian integral actually vanishes along any cycle in the homotopy group. Yes, and it allows us to define by integration a univalued function, which also will be holomorphic. This univalued function will be this R here. And this allows us to have this expression, solving the tangential Poincaré focus center problem. So if you have this M1 vanishing along one vanishing cycle, you get it vanish along any cycle in this Riemann surface, and then eta have to be of this form, which is called algebraic exact form. Yeah, it's almost exact form, relative algebraic exact form. Yes, only by this new extra term we have. But well, like maybe I can write it here. Yeah, algebraic exact form, relative exact form. But if you add also some thinking about this center condition, if you add this condition on the degree, let's say the degree of the deformation, if you impose also that the degree of the deformation is smaller than the degree of the differential of the Hamiltonian, this term does not appear. And it means that with the first Melnikov function vanishing, you get that the deformation is just, it must be an exact form. But remember, we had that the whole deformation was written like this. And that it means that the whole foliation actually was given by the differential of something, polynomial. It imposed that you preserve the center. So it is very strong because only with the first condition you end up with the center. No? This is the kind of situation we want to study. And it happens only on the generic. Here is on the generic assumptions. Okay. So probably questions. No? Okay. And so let's continue. Okay. So let's say until here we already understand what's happening when we work only on the level of the first non-zero Melnikov function. But what happens if you are not under generic conditions? Then it means you have to go to the next step, to the next order. Not here we understand what's happening until this level. But if it is identically zero, but not generic, then you have to study the next Melnikov function, the next order. So we want to understand, we understand very well that this is an abelian integral, but what happens with the next order? And this is given by this result, given by Pontryagin, François, and Gavrilov. And they gave an explicit expression for higher order Melnikov function, and it's given by something that is called iterated integral that I will explain. I can erase here. Okay, it's very similar to the first case. Let me just give you an idea of the first step, and then the rest is very similar. There is a trick here. Well, okay. This is, okay. Under this assumption, assume that M1 is identically 0, and that we already have that eta can be written in this way. Okay. And then we want to compute the second order Melnikov function. And to do so, we will integrate along this cycle this foliation multiplied by something, df plus epsilon eta. I can, if I multiply by something, it's the same foliation, so it will be 0 again, because it is tangent to this differential form. And here, it is convenient to multiply by 1 minus epsilon g, the g which is given here. And, okay, so we get this, multiplying by 1, and then epsilon, so we have minus epsilon g df and minus epsilon square g eta. this is equal to 0. But GDF is eta minus dr. So I can change this part. Okay, so this part will vanish. I have here epsilon eta, and I will have minus epsilon eta. So now we have the F. And we saw that this part is already delta, the displacement map. And this plus epsilon integral dr along gamma epsilon. This was minus epsilon square g eta, the integral. This is equal to 0. And this part here is of order, the same order. This part here is of the same order as the displacement map. So this is of order epsilon cube. So we have this. So we have the displacement map. Okay, we have df gamma epsilon. It's equal to the displacement map, which is equal to epsilon square m2, because I am assuming this m1 is already identically 0. M2 plus higher order terms on epsilon, and this is equal to epsilon square, the integral of g multiplying by eta along this this cycle. After, if we derive this 2 times and we take the limit of epsilon going to 0, then we conclude that m2 with respect to gamma is equal to this integral, the integral of gamma t of g eta. Okay? But let's have a look to this g function. So we had from the beginning, after the first condition, that eta was given by g multiplying by df plus dr. If we take here the differential of eta, we have dg wedge df, and this is what we call this Gelfand-Leray derivative. It is like dividing by df, but this is the definition. Yeah. This eta prime, it's given by that function, that differential form, which satisfies this equality, which geometrically we can read it like something that is on the perpendicular direction of the Riemann surfaces defined by f. And in this particular situation, this eta prime is just given by the differential of g, and this is from we get this expression. Actually, these are almost the same. This is already what we call a iterated integral, which is defined here, which is just nested integrals. You start, you do the first integral along the first differential form here. After you integrate that form, you multiply by the second one, and then you integrate, and so on. So this is the same as it is here, plus g on the initial point, I will call it p. So it's almost the same. I can show this equal to 0, so they are equal. Okay? And this is, at least on the second order, why you have this kind of expression. You repeat the situation for the order you want to express here. But there is something not very useful here, that this expression depends on the order explicitly. If you go to order 3, then you will get 3 iterated integrals here, and so on. And this gives us a more complicated expression of the Melnikov function, because it is kind of difficult to deal with if you have a iterated integral of bigger length than a smaller length. Because let's say these iterated integrals, they are like the generalization of the RAM homomorphism that relates holonomy, homology with homology. But on the level of homotopy, it means if you have an iterated integral of length 2, for example, write it here. So when we had those abelian integrals, they were just the RAM homomorphism. But once you have, let's say, something like this, it is an iterated integral of length 2, this is the dual of a commutator. Let's say delta 1, delta 2, where delta 1 and delta 2, they belong to the first homotopy group of a regular fiber. Okay. And what does it mean? It is dual in the sense that if we integrate this expression along a commutator, it doesn't vanish. So it detects, it tells us when you have a commutator or not. And abelian integrals, on the other hand, they don't see at all the commutators. And this is important here because, as we said before, many of the information of the Melnikov function is concentrated on this orbit under monodromy. But the orbit under monodromy is a very complicated object because it is just a subgroup of this first homotopy group. And it contains a lot of commutators, and you have to understand how they are involved in the Melnikov function. For example, if the Melnikov functions detect this commutator, at least you know that it has to have a length equal or bigger than 2. Okay? So at this point, it is important to understand what is the exact length of the Melnikov function. So let me go back a little bit. As I said before, a priori, the Melnikov function should be an iterated integral of length at most the order, but in 2018, we proved with Papa Martes, Dmitry Novikov, and Laura Ortiz that we found a bound, an upper bound for the length of the first non-zero Melnikov function, and a length that it does not depend on the perturbation. So it depends more on the geometry of the Hamiltonian, and it depends also on the orbit under monodromy of the cycle. And it turns out that it is defined here, we call it the orbit depth, which is just like detecting the commutators that live on the orbit. You make this orbit under monodromy, and you determine if this commutator on the orbit belongs to this group, which is the commutator of the orbit with the first homotopy group, and you define this number like that. Okay. And for example, in the generic case, after we can compute it, in the generic situation, we have that the orbit depth is equal to 1, which corresponds with what we had before. This is just abelian integrals. But in non-generic cases, let's say where the Hamiltonian is given by a product of some linear terms, it's like a product of lines on general position. Let's say the picture on the real plane would be something like this. Etc. Some lines on the general position. In that case, this orbit depth is given by 2. And it's very good bound, because even if you're working with, let's say, the 1000 order Melnikov function, you know this is not a 1000 iterated integral. This is just an iterated integral of length 2, and it allows you to understand a little bit. You can deal better with this kind of integral than with 1000 length iterated integral. So at this moment we have, this is, as far as I know, the best upper bound for the length of Melnikov functions. But recently we started to study not only the first Melnikov function, but all of them, the whole world of Melnikov functions, to understand them as to give them some structure and to identify the length of all of them. This is the next result here. So again, we start with the polynomial and a loop on a regular level curve. And for any perturbation, you can give some conditions. Let's say for any k on naturals, you can find another natural number such that the length as iterated integrals of the Melnikov functions, they will vanish. Well, if you have the first n vanishing, then you have a decrease, a drop of the length of the rest of them by k. You decrease the length for an infinite number of Melnikov functions in this by this number. How much time I have? 5 minutes. Okay. Maybe I just give a little bit the idea of the proof. So the idea is, well, here I have commutators on the orbit of length 1, which this is homology, or length 2, which is commutators of this type, and so on. I have the commutators that I can find on the orbit, and I associate the Melnikov functions that correspond to these cycles that belongs to these places. And here we will consider some, I will call them, they are ideals of some differential algebra that we define. So we have these ideals generated by the diagonals. This diagonal corresponding to 1, 1, 2, 2, 3, 3, 4, 4, and so on. The second diagonal. And we use, well, let's say in the first diagonal, all these elements, they can be expressed with Wronskians, which means they belong to some differential algebra, which is generated by abelian integrals. So you can express this with abelian integrals and their derivative. And then we can use this result by Reed and Randenbosch, which tells that on a differential algebra, finitely generated, you have this kind of Noetherianity property on the radicals, on the radical ideals on this algebra. And going back to this picture, then we said they were given by Wronskian, so they belong to a differential algebra. It means they have this notoriety, and you only need a finite number of them vanishing to have all of them vanishing. And in that way, you decrease the length of the Melnikov function, the length of the Melnikov functions, because if this vanish, it means this cannot be of length 2, because it vanishes on commutators of length 2. And you do the same with the rest of the diagonals. There are some, it is not straightforward, because in this level we had this property of the Wronskians, but for the rest of them you have to prove that also there exists a differential algebra. And so we work with some differential operators to prove that there is also a differential algebra for the whole, for any diagonal we had before. And I think I will finish here.
Thank you for a nice talk. Any questions, comments? Yes, please.
There was a appearance of the Chen's iterated integral formula, and then in my experience, that was often used as kind of an algebraic term, because it commutes with concatenation if you kind of chain these integrals together. And I was wondering if that comes into the proof at some stage, or if it's related to this process of elongating these links, if it's possible to kind of commute before or after.
So you're talking about the Chen homotopy theory?
The iterated integrals.
Yes. Like here, no?
Yes. This is where it comes in.
Yes. Yes. We can see it just like the RAM homotopy theory. Yeah.
Okay, and then do you break your space down into these nilpotent groups, or these central sequence? Does this come into play when you're analyzing the growth of this
Yes.
factor?
Yeah, I passed here very fast, but this is crucial. These commutators are given by this lower center sequence, and it happens that if you take this quotient, let's say just commutator of exactly length j, then the iterated integrals of length j, they are the duals in the way I said here. Yeah.
Okay, thank you.
Yeah, and with this Melnikov function, we are restricted ourselves to only commutators that live on the orbit for the moment.
So, any other question, comments? So I was wondering, if you get this upper bound for the original problem, how hard would it be to get the optimal bound?
The upper bound for limit cycles.
Yes.
For the original problem, do you mean the classical 60th, Gilbert? Okay, so you're asking if we have this upper bound for any polynomial differential equation?
Exactly. So you have so the problem is stated that some bound, right? But can you get an optimal one? So it's
Okay. No, it's not straightforward. Actually, well, even for the infinitesimal, they have already an upper bound, but it's very, very non-optimal.
But then why should he pose it this way? So it's like only one bound. So
because there are two steps on the proof. You have to prove the existence of the bound uniformly depending on the degree, and then you bring an explicit bound and you try to get it optimal. But it's not easy. Actually, in the infinitesimal version, they have this optimal, but the authors, they said that with the tools they have, they cannot get it optimal. We need to develop more new techniques in order to get this optimal bound. So it's a hard question. Okay.
Thank you very much. So please, let's spank again.
Thank you.